Very nice. Okay. And the recordings will be available for you, for anyone else who you want to share it with. I have no objections if you want to share with friends or people interested in category theory. So today's lecture will be mostly a crash course in the things that we all already know, but to have a solid common ground and to know how to progress. We need to establish some terminology, some notations, and then we can go to more advanced topics in the next lectures. So first, for lectures that you saw in the course, up to limits, will be pretty much usual. Will be pretty much about the usual stuff that you do in everyday algebra when you are writing your thesis, when you are looking to some papers, whatever you're doing. So, but still, it has some interesting points that usually are not pointed out or are pointed out without appropriate attention. After the lecture number 4, we will go more in a so-called coherent calculus, and we will be applying a lot of we'll be applying this calculus a lot to establish the common framework in which pretty much all the known concepts will fall, so-called tensor situations. Well, if people say that something is universal, they usually are referring to some big property from which follow most of the other properties and theorems that that are used. Right now, in my personal opinion, after studying and writing my thesis, I will say that I found the point from which comes Ken extensions. So from which Ken extensions can be derived, and by well-known slogan of Sanders MacLean, all concepts are Ken extensions. So if something is higher than Ken extensions and also covers some other things, why won't we talk about this and use this to some topics? So let's then start. We will start with the we will call it what is the category. So first part will be called small and small category. I won't be given the super precise with all details definition of every concept, because right now these concepts all are very well known by everyone here, but still I will be drawing something and pointing out like the main features with the bullet points and every definition. So what is a category? Category C. So I will be writing categories with script letters. So the categories can be written as, let me write here my script letter that you will familiarize. So A, B, C, D, E, F, G, etc. So like this is my script. Well, U, X, Y, Z. So like these letters all will be used for to denote categories. Okay, so category C consists of the following data. Now I will write this data. A class of objects. Row of C, and in parentheses I will write that just C sometimes. If we understand that we are referring to objects. For every pair of objects X, Y belonging to this class objects of C, we have a set of morphisms in C from X, Y, that Sometimes the set also will be denoted as xy or xy. Just not to write every time the word more, but I want to tell you that in different literature you can find different conventions. Some people write home here. Some people will write here the precise name of category, as I wrote here C, etc. The third point, for every triple of objects x, y, z, we have a function which called composition law. So it takes sets and gives a result in a set. This function we can call C small sub x, y, z. And we call it composition. Basically, what is it doing? It is taking the pair. So first, here we have pair from y to z. Second argument is from x to y. This is G, this is F, and it goes to from X to Z, which is GF. And subject to conditions that I will just mention, everybody knows them. So, oh yeah, I forgot, and identity morphisms. And for every X, there exists an arrow 1 sub X belonging to X X. That composition is second. Composition with identity law. Everybody knows composition with identity gives a given function. And the last one, if I'm not wrong, that home sets are not intersect. So if we have the pair y is not equal to pair y prime, then x y intersection with c prime y prime. And so we can uniquely distinguish the beginning and the end of every morphism. We can have that we have a morphism that belongs to two home sets. So it's as was in school. What is a function? Function is a law that takes elements from one set and brings them to the other set. So every function, morphisms we are considered as something like functions or some connections between the beginning and it starts has where it starts and where it ends. Next to one. So why we have this? Okay, this is well-known notion, but I want to point out certain things that we will be changing in this course. Well, first of all, mark. X, Y. So sometimes people like to use all the axioms of a category, but they want to drop down the word set. So to have a class, so more than set of morphisms. So when we have x, y set, then C will be called locally small categories. I will take locally small in parentheses because every time as people write categories, they assume that it's locally small. So this was locally small categories. Second thing, by the way, anytime you have any questions, please interrupt me at any point. We can stop and even finish the lecture at that point. So start talking about the thing. If something is not understood, our goal is here to learn, not just me to mumble something and you will sit and finish the lecture. Okay. Second, if C x y is not necessary, I said that we can. There is a C is a big category. Third, I wrote that objects form a class, so we cannot necessarily make a set out of the all objects. There can be more than a set. But in case that objects of C is a set, from this will necessarily follow. Not necessarily from this we. So in this case, we say that category C is small. Today, later, we will see that there is a certain type that compromise between small category and just locally small category, which is essentially small. But it will be later. Okay, that's one. Second thing is the following: that every morphism, identity morphism, belongs to the set from X to X. Okay, but what we have here, we have a choice. Every choice of an element can be stated differently as a function. Our goal in this course is to learn how to functionally think, or even functorial, not point set wise. X belongs to Y, Y belongs to Z, X belongs to Z, no, in arrows and in terms of diagrams. We'll have diagrams later. So the fact that 1x belongs to C, X to X, it is the same as to say that there exists. I will put existing quantifier here. There exists an arrow from a singleton to CXX. And this arrow has a name. It is also called 1x. So the choice of element in the set, it is the same as a function from a singleton to your set. So we should always think of identity as a choice from CXX. Okay. And the fifth remark will be the following: that we have a composition law, and we have a certain way how to think about it, that it takes an arrow from X to Y, then from Y to Z, and compose them. But always what is required that there exists this composition law. How it works, it depends on a category, so not necessarily your arrows are functions between sets. It can be something. And this something we understood as we write it as an arrow, but not necessarily this way. The composition here is written in a usual order, but there is other order called diagrammatic. So when I will write X, Y, Z, the composition will be G. But I also can write it in a different way. So this is a usual order. But I also can write it as X, Y, Z. Here is F, here is G. And semicolon G. People usually write semicolon G. It has some origins in computer science. And this will be called diagrammatic order. Diagrammatic order has benefit that it's easy to write and to read. Usual order has advantage as we always think as here goes our argument and we apply. So this is more common and useful in standard usual classical math. This is more used by computer science, but in every article usually it's said what convention that the author used. Okay, so these were just some very basics. Are there any questions? Yes.
So we are always concerned about body mark 1 and 2. So we are always sometimes concerned about the collection of morphisms being a set. You have what kind of problem like
choice. If it's not, so if from a set we can pick up. From a set we are using axiom of choice. We can pick up an element. If a class, we can state that there exists. So there we will arrive in at least this one set theoretical issue. Another one that all the theories that we usually know and in our subconscious is set theory. We are thinking in the axioms of set theory that we used all the years up to today. When we start using classes without axiom of choice, we should give constructive proofs. We can state that something exists. If exists, please give me. Or tell about any. If any, that's fine. So you can pick in, but picking any. But you can pick up some particulars somewhere there exist. That's what we arrive in. It's a set theoretical issue. I don't think that this is the only one. I mean, but this is the main. But there are other questions. Okay. Well, then right now let's write a couple of categories to have in mind their common name. We will use them very quickly. So first of all, I will make a couple of columns. Here will be called name. Here object. Here will be the first category will be set. Category of sets. Objects are sets. Morphisms are functions. Also want to note for you that functions are assumed to be everywhere defined. So if you have function from x to y, then it's defined for every x. Well, when you had in school function y equals 1 over x, it's not everywhere defined function from R to R, from reals to reals, okay? Because it's without zero. So this won't be a function. It will be a function on a subset, but not on a set. We consider only function, okay? Well, the first. Second one. Objects are abelian groups. And morphisms are homomorphisms. Homomorphisms I will usually write HMM. Too short. After abelian groups, let's write some other well-known GRP or groups. So here are groups and again homomorphisms or groups. Well, whom else we will immediately should think of? Topology. Objects are topological spaces. Morphisms are continuous maps. Next, H. Objects are spaces. Morphisms are classes of continuous maps. In all previous examples, we had functions with certain properties. Functions as in sets. Here, they are not functions. It's a set which consists of classes. So, a representative for every homotopy class of continuous maps. So, all these were functions. This is not. So, this morphism set does not consist of functions. It consists of elements, but not functions. Okay. Where's my list? Some people are interested in partial ordered sets, or sets. So objects are partial ordered sets, and morphisms are ordered preserved. Then rings. So we will assume that it's associated rings with identity and homomorphism rings. Then let's look at some more specific categories. Let's look at empty set. Empty set is a category. It has empty class of objects. Then objects, we don't have objects. And since we don't have objects, we cannot pick up home sets. So they are empty, but empty set is a set. So morphisms are not. It's just empty picture. That's fine, but it works. Then category consisting of one point. Let's call it breakdown star. I will call this category a different name in a few minutes. It has one object and morphism, only one. This is a picture of code category. So only one identity morphism. Okay. Then we have category with two elements, but not one. I mean, here, or well, on empty category, yes, you can do much, but on one point category, you can define other set of morphisms. For instance, will be identity and the other morphism, which is squared to one. So we will have Z2 as set of morphisms, okay, possible. But I just wrote trivial. Then other one will be 0. Let's call this category 1. This category we call 0. So because it has only one element 0, category named by this one. I will explain later why this way. We'll have objects 0 and 1, and one arrow from 0 to 1, and an arrow identity on 0, identity on 1. Then I'll continue. Then we have category N. This category we have object 0, 1, etc. to N. And we have arrows from 0 to 1, from 1 to 2, and to N. What I'm missing here are compositions. Also, we have arrow from 0 to 2, from 0 to 3, etc. But they are given by compositions of this small arrow. So the arrow exists. There is a unique arrow from I to J if and only if I is less or equals than J. I'm omitting compositions. I'm omitting identities. We do not need all the time to care about identities. They are always present. And compositions, we always can add them there. But to write as a quiver it, very plain with the quiver, it's convenient in this. If we have a set, any partially ordered set, even we don't need to post it, we need pre-ordered. So what does it mean? That we have reflexivity and transitivity. Then objects are, again, elements of A, and there exists unique arrow from A to A prime, if and only if A is less or equal than A prime. What I'm doing here wrong, I should write not A, but A, comma, order. Because partial order set comes with its order. On every set, you can determine many orders. You can determine trivial order. Every element is less or equal than self, period. You can, by Zermelo theorem, make a total order. So to order all elements of any set, even complex numbers. You know that there is no particular order on complex numbers, but theoretically all complex numbers can be ordered. Theoretically. This is where axiom of choice is used. So any preorder set becomes a category. And all other examples, this n, 1, star, 0, are just instances of this. And then one more example. Consider m, comma, multiply a monoid. I'll remind that monoid is a set with a binary operation. This binary operation is associative and it has identity. So if I wrote monoid here, I put composition and I need to put also an element 1. Elements of this category associated to monoid will be only one element, singleton. And on this singleton, we define morphisms to be precisely the elements of monoid. So here the set will be M, and on this arrow we take element M. And how is given composition? So if you have a M, of course from dot to dot, dot is our unique element there. Dot to dot, here is the M prime. Here we will write a composition. Composition will be M prime M. You will ask me why I do not write M prime. Does it matter? Well, of course, answer is no, but you will obtain so-called opposite category. Okay? So what is opposite category? We are still going by examples. So opposite category has the same set of objects. It's written CO. Objects are the same, but morphisms. So CO from X to Y is defined to be C from Y to X. So when we will write in this order, we will obtain our regular category. I mean, the category that I just defined before. When I will write in a diagrammatic order, we will obtain opposite category. Because arrows are composed in a different way. An identity of monoid certain as an identity of my one element category. So one element category has only one identity morphism, and it's given by this. Okay. Are there some things I forgot to tell you? Well, yes, a little more sophisticated thing. A category of small categories. Cat. So cat, it's not an animal. Well, it's quite rare, not rare. It's quite frequently found animal in this whole zoo that we will be dealing with. It consists of small categories. And morphisms between small categories are functors. Well, the functors we will talk very soon. Okay. Well, you will also say that between functors you have natural transformations. So then, as it's written, I forgot by whom. Professor Marcinkowski will be is right now around. He will help us and say that in some book it's written that categories are invented only for a purpose, for functors to land in. So we actually need functors. So theory not of categories but of functors. And a little more to think. It's not even about the function; it's about natural transformations. So here are natural transformations. But you will ask me, I do not have such column. My bad. I didn't do it before because I did not state what is another level of a category. Before I was talking about a category, but to add natural transformations, category of small categories, I need to a little go deeper in definition and define so-called two category. But with the two category, we will, I hope, finish today, but not right now. But I want to show you that the number of columns grows, and you can have n columns, you can have infinity columns. And the main point is that the arrows on different labels that do not only exist, but they should agree with each other. So they work together. There are identities on previous levels that work as identities for the second level. For instance, here, identity functor on a small category composed with another functor will give that functor, but identity functor comes from a category. So element from first column will give us some trivial element in the second column, and so on. This one thing. Another associativity. And another one is that the parentheses should be moved in the way that we like. But there again will come another issue. What if they move up to isomorphism? In many cases, like in homotopy theory, they will move just equivalently, but not equally. What should we do? And then we will get another notion, not of two categories, but of bi-category, and so on and so forth. So category theory goes infinitely in the direction of number of columns and the relations between different types of morphisms. So sometimes we cannot say that composition of two arrows will be equal to third. We can say that it's only up to some natural law. Sometimes this natural law is an isomorphic invertible, sometimes just some particular kind of morphisms that work together with everything else. But let's return to kindergarten. After categories, we will consider category by mod, category, because it has objects. Rings. Identity. You'll ask me, well, I have associative rings with identity here. What's the problem? What should I do? What will be my morphisms? Never think about that this way. So morphisms will be bimodules. So bimodule M from ring L to ring gamma. You have one dot is one ring, another is another ring, and between them you write arrow. This arrow has just a label, it's not a function. That's a label, so relation from first element to another. This label is this arrow is labeled by bimodule that has on one side lambda structure, on another gamma structure. So it's a left lambda module, right gamma module, and the structure is agreed by the generalized associative. Or I don't know how the taxon is called. That lambda m gamma can be computed in either way. Well, what will be there? Here will be homomorphism or bimorphism.
What's the composition? What's the composition for the bimodules?
How the composition is done of arrows? Well, you asked me the question that I was always looking to, because it's a particularly good question. Nobody asked the question about composition before. No, that's not I'm criticizing anyone, I'm just asking that. Before it was clear, what's the composition of arrow? Well, fine. The composition here, I said about transitivity, maybe everyone thought that transitivity is here, composition, important. Functors, yeah, composition of functor is a functor. In an opposite category, well, fine, everybody probably saw opposite category. What will be here? Huh? Exactly. It's a tensor product, that's right. Our all good friend. So if we have lambda gamma, which ring? Give me some Greek letter, sigma. So here is m lambda gamma. Here is n gamma sigma. Here will be m tensor n over gamma. And it is a left lambda, right sigma module. Because the structure, gamma structure here is, how it's said, convolved. So we are like using a convolution. We are absorbing this gamma structure inside to convert the pair Mn into one module. But this lambda structure on the left and sigma on the right opposite. That's a composition. So composition is given by the tensor product. And composition given by the tensor product works well. How well we will define in a couple of minutes with the homomorphisms of bimorphism. Okay. So we are almost finished, except that I want to give you a couple more notions, just as examples. So let me give you 1, 2, 3. So here will be product of categories. Product of category C cross D. Objects are pairs D belonging to of D, and morphism sets are, is no surprise. So morphism from C, D to is given by C small to C small, where from C to C prime is C small, and from D to C prime is D small. We're just going component wise. This is the product of categories. Please underline the word product, because the next word will be coproduct. And I'm writing this thing. Square cup. Square cup, not cap. Square cup. So objects are disjoint union with a class They do not need to be small. It's just disjoint union of classes. And arrows are, well, let's write the following. The same arrows as in C and D. How you can imagine this? Draw your one category, C, draw your second category, D, circle them around, you have the whole category. New category is a couple. So it's a category where there is no interaction between C and D, but the objects and morphisms live together. Well, that's like people who hate each other, but they still need to live in one building. They try not to intersect in the kitchen, in the bathroom, in the basement, in the parking spot, but they know about each other, but there are no relations. Well, this is enough with categories. Now we'll go to functors and natural transformations. Probably so that at the beginning it will be just definition of a category, plan, slowly, every category, no. Same stuff will happen now. So I will give a definition of a functor from one side, but then we will try to look in a couple more examples, not very in details, but they should tell us something. So finish categories. Then functor. What consists of functor? Functions. Well, let's not call it function map. Because functions usually are related to sets. Map of C. We should call it again F. This time I'm using notation, you should call it F sub 0, whatever. Then for any x1, we'll give C a map y to D y. I call it F sub xy. Such that now you'll see as a surprise. So I want to write down, because we have a course with surprise, so right now I will give you a surprise. I will write F for my G, sorry. F of, let's write it. X to Y Z F G S F to X Y by F F Y to Z. Right? It's the usual axiom of functor that the composition, functor of composition is composition of images. I want to little think about you and tell you how to think about this Functorial. What's the problem with this? Well, honestly, nothing up to now. But later we will have problem with that huge, much later. The problem is that we should pick up some elements, so we are giving point-wise property. It's a problem. You should not give point-wise property. You should give functorial properties that are stated in terms of factors and natural transformations. So what should we do? We are taking a pair. First element of pair is, oh, well, by the way, I did a mistake here. Can you see? They should be swapped because the composition is GF. Here we'll get composition FG. Try to have some errors. I don't need to see any. So what are we doing? We are taking a pair GF. Then this pair GF is mapped to a composition GF from one side. From another side, it is mapped to pair of images. Then we take a composition. Take image of composition, and we compare it with a composition of images. So here is a composition in a category C, sub X, Y, Z. Here is what composition superscript category D sub X, Y, and Z. Okay. Here is a function that takes first component to first, second to second. So it's a Cartesian product of functions. What are these functions? Here. So it's first f y z cross f x y. And here I just have this function, this prescribed function between more sets of morphisms. So here's f. Okay. Well, right now you will probably, once you will first see this thing, you'll never recognize that it just functor preserves composition. But now I will show you that you should think as a computer pretty much. To write Functorial, to think Functorial, to work Functorial, to get results that are immediately natural, immediately multi-setting applied, immediately maybe corrective, vary with a foresight, and so on. Try to think Functorial about anything you do without a choice. And then you will see that there is no, very often, not always, but very often, there is no need in element-wise stuff or set theory. You can just use it with whatever. Let's write down this thing. It's this square to use. So when computes, I will write just equal in the middle equals square, set it's commutative orally. Let's write down how to look the axioms. So C, Y, Z, cross C, Y goes to D, Y, Z. D, Y. Now, it's D, F. Square is commutative. The composition. C and here is composition in a category. Such that was first, and there's a second part of my such that. What is it? That f identity on X is identity on Fx. Well, we know what's identity. It's a choice. So we are taking a singleton from a set X to X. And also we are taking it. So this is 1x. We take an identity from a set of morphisms from fx to fx. And between them who lives? Our old friend, functor. It's component of a functor for x and y. But here will be. And this square commutes. Why did this definition in such a complicated way? Because in a couple lectures we will have so-called enriched category. And for between enriched categories we have enriched functors. That's precisely the definition of enriched functor, which does not use element-wise stuff. And also, you can see what is to think functorial, what is functorial way of writing. Of course, after this, you have remarks. So, from CO to Z, it's called contravariant functor. To write a contravariant functor, you need a little to think about this composition. There will be additional arrow theorem which swaps the pair. It's okay, this happens. Just don't want to spend right now time, you can do this as a homework, or just look and find it in some literature. In a list of reference, you always can find a lot of friendly books in which you can find something more or less difficult. It always you can ask me. So try to write yourself. I'm not giving anyone exercise, I'm just giving you advice. If you want to think how to write contravariant functor, make yourself an exercise. Write the composition axiom that contravariant functor change the order using diagrams. Well, this was one thing. What's the next? Oh yeah, what is the next? The next is that I should give you a couple examples of functors and tell you what's the composition. So composition of functors. Composition of functors. Nothing surprising. You have category C, category D, category E, unit functor F, unit functor capital G. Then object C goes to C, goes to G, and C. As you see, I'm very often writing functor of an object without parentheses if it's understandable who is a functor, who is an object. So who is between the letters and argument, I'm omitting parentheses. Later, I will use even different so-called Einstein notation, and I will be writing covariant arguments as a subscript and contravariant as a superscript. This will be later. Right now, today, I won't be doing it. And function, okay, and what? If you have a morphism from C to C prime, morphism F, it will go to morphism from F to C prime F. C of small f. So that's how works composition of functors. If you are thinking in a way of the previous definition, that you should write here arrow where E, G, X, Y, and here will be G, sub Fx. Composition of a functor is a functor whose maps on objects are composition of maps between classes and maps between sets of morphisms are given by this composition. That's all. And then it's as an exercise to check this axiom hold or not. Okay, and that's with functor examples. I'll give just a few examples, otherwise we will stop the lecture at this point. I'm running a little bit slow as I see. But anyways, first of all, let's think about some trivial cases of functors, right? When we are starting looking at any notion, we always are interested in the easiest of the notions. We are interested in some trivial cases, or in other way of thinking is the defined class of objects empty or not. It's a general math advice for everyone, and for me and for myself too. When we are working and trying to prove some theorem about something, I think other objects you are working with, because on empty set you can prove any theorem, and it's contradiction. It's a theorem from logic. So if you have an empty class of objects, you can prove both theorem and its contradiction. So that's not a math. Okay, so always think other such objects. First of all, we need to find some function. So identity functor from C to C. Also the functor I will write as a boldface C, boldface 1 sub C. Or if it's understandable, just with this bold one. It's an identity functor. What does it do? Nothing. Just kept everything as it was. Second functor. Let's call it. So we have C category and consider object D in D. As you see right now, I'm writing not ob D, but I already wrote this here. X, Y belong to C, so I'm writing object there D. So what is it? What I'm talking about? I'm talking about constant functors. Constant functor with value D. You're taking category C. You're taking category D. You're taking any object C, and it goes to D. You are taking any morphism F, and it goes to identity on D. So whatever you do, you always get D. Always. This functor I will write delta sub D small. So this functor, let's write delta sub D. Okay. Well, we are trying to think functorially. So what I did some very dirty stuff. I picked up an object from a category. And well, it's not bad, but Maybe we can do some sort of, more tricky way how to think of picking up an object. Example C.
We just a counter from that zero category.
Yeah. Stop reading my mind. Okay, anyone can. Of course, it's from 0 to category D. And it takes object 0 to object D and an identity arrow on 0 because there are no other arrows. Identity on D. This functor I would call, without any surprise, letter D. Well, it's a name. It's a name for the thing. Definitely, this factor will always be constant, by the way. Without doubt, it has the same stuff as this. It's also constant factor. So from a trivial category, or trivial one-point category, usually when people say trivial category, yes, they think about this one, not about empty. About empty, we will say not trivial category empty. But about this, let's think that it's trivial. Well, I'm not satisfied because I started from a trivial and I ended up somewhere. What if I will start from C and end up here? What will be? C trivial. What it will be? Any of this. We have no choice. We have no choice. As a little math folklore, I would say that you can take a function from empty set. This has no arguments. It's constant, right? To somewhere. But you cannot land in an empty set. Because a function, by its definition or everything, should land and give you something. It cannot just stay with empty, with open mouth and say, "Hey, what should I do with you?" No, all the functions are giving results. So here we have no choice except this: 0 and 1 sub 0. Therefore, I can write the constant functor uses this factorization, this triangle commute. How I will call this arrow? Who knows? How I will denote it? Because it's unique. That's it. You don't have it. When you have a unique arrow, you usually either write exclamation mark or shrink, or just nothing, because it's understandable what's that. That's it. Okay, it was an example 2, let's be not 3 but 2 prime. 3. Forget it. Forget for fun. When we have category whose objects are sets with some additional structure, we can forget it. Just erase. For instance, Rabian groups get to sets. Forget that we had not composition know how it's addition operation on a set. Forget it. We can have from group to set column set. Okay. get to set, you have category of small categories. Take a small category. Small category has underlying set of objects. This function is called ob. This is ob, our objects, etc. These are all forgetful functors. You can take from poset to set. Just forget partial order. Whatever. So these are types of forgetful functors. They do nothing on morphisms. They preserve composition because composition is going between the sets. Composition law is kept between functions on level for morphisms, blah, blah, blah. Okay? But we forget that it should satisfy some properties. We erase the axioms. We erase such that. But without this such that, we get, let's say, the free functor. Called free functor. Set to let's call it script f, right? Not a category, right? Let's just use a script letter f since it wasn't used. So it gets set s to what? To a free abelian group on a set s. We have yeah, oh sorry, set to count. S is going to a discrete category. Oh no, discrete is not K, we don't see. Okay, discrete category. What is a discrete category? We haven't said. Discrete category is a category whose morphisms are only trivial, only identities. Okay? In discrete category is a category where between every pair of objects exists only at exactly one morphism. It's indiscrete. We'll talk about them a little later about this case. Etc. For groups, it's a free group function, so making a free group on an alphabet. For topology, discrete topological space, and so on. How they relate? Use its adjunction. What is this adjunction? We'll see it much later. I mean, in a couple of meetings. Okay, this is all with functors, I think. And yes, now we are going to natural transformation. Natural transformations are so natural that you call them natural. Why it's natural? Because there is some law where we observe a law of nature. It doesn't matter to whom it is applied. Because law just exists. Okay. So part 3. The second part is called functors. This natural transformation. So we have C, E categories. We have functor F, functor G. It's a pair of functions. Between this pair of functors, we want to define an action. This action, which moves F to G, we call natural transformation. From F double arrow to G. So natural transformations, not always, but usually are denoted with double arrows. Or in tech, it's backslash capital right arrow. Natural transformation. Consists of data. As you see, I never said the category is a something, or functor is a something. It's a set of data. So it consists of certain data. Even the word set, I won't like here. I will say collection. Consists of data. Arrows. From 1 point set to E. X G X sub X. Such that and right now I have a choice either to give this definition a couple more or explain to you how to write functorially as a square that I'm going to write that everybody knows. What should I do? There are 5 people, you can always vote and some part will always win. So should I write and explain functorial with this definition, or should I give this definition and a couple more? I mean, the definitions, notions, examples. We have 15 minutes left. Well, by the way, if somebody is not in a hurry, we can stay a little longer and cover more. I mean, we are here to learn, not to pass. So let's start from second question. How long who wants to stay? Till 1:15 or longer? Who wants when? You can leave any second.
Yeah, no
You
problem
can.
staying.
You?
I just have something at 1:30, but that's okay. Sorry.
So we finish at 1:30 or before it. Or you haven't come?
Yeah, I have to go back to Nightingale Hall at 1:30 to teach someone.
Okay, so 1:25 upper bound.
Okay, yeah, sure.
You?
I can stay.
You?
I may head out. I haven't had lunch yet, and
Well,
yeah.
you want to grab pizza?
Um.
I'm joking. You know what I mean.
Yeah.
That's okay. So let's run until 1:25. Other times, if you people want, then I'm just glad to finish what I suppose. So I'm never going to keep anyone till the night, but still, if there is something to finish, we can finish. Okay. So then I return to the first question: should I go in a very elaborate hexagon, or to give a couple more definitions? Because to the hexagon we will return if this was way later. But maybe here it's in time, or what do you think?
I want to see the hexagon.
You want to see the hexagon? Oh, okay. You want to see the hexagon? Sure, yeah. Sure. I see a lot of masochists here. Okay, this life is full of pain, and I will show you right now how is the pain. So, to understand that this hexagon appears not from nowhere, that I'm going to fill here, we need to write usual stuff. So for any arrow from X to Y, F, we have F, X to F, Y, X, F, here alpha sub X, here alpha sub Y, G of Y, F of Y, down G of X, G of F. Yes, here we have this. What are we doing? First of all, we need to go this way and go that way and state that these both ways are equal. So we need to take alpha sub x, comma, g of f. Then bring them where? To their composition. Gf composition alpha sub x. Here, to pick up. Well, does the order matter? 1 second. Yes, the order matters. So I should change here the order. Alpha sub x. Here will be alpha sub y, comma, f of x. Here is f. Alpha sub y composition f. And they say that they are equal. But we need to pick up these guys. Where are we starting? We are starting from the set of morphisms because we have this thing, right? This thing belongs to Cxy. So C, y. Here comes f. Then we need to pick up Gf and alpha x. So to pick up Gf, it's easy. But to pick up alpha x, we need an arrow from one point set to here, to this home object, to this set of morphisms. Okay. Therefore, I see that I have two arrows, but with different sources and targets. What can I do? I can take Cartesian product of two arrows. Look how it will be. So here I write Cxy equals 1 point set. Then it goes arrow to d x cross d of x. On the lower level. Again, I can't just pick up immediately pair. I need to have a function. I need to have a spot where starts alpha sub y. But here, it should go as the first component. This begin. Then I'm writing cross xy. Then xy cross d x 1. And finally here d f x gy. Here are isomorphisms. Because Cartesian product with 1 point set is a pointless operation. Let's call it this way. Here is g y cross alpha sub x. Here alpha sub y cross f x y. Here is a composition in category D. Here is composition in category D. Between whom? Too much to write. This triangle computer. So I'm taking function f, then f goes to pair f comma star, this pair goes to gx alpha x. This goes, you know, here f goes to f star comma f. This thing gets to alpha sub y. And this goes, you know, it's how internally it works. Well, it was quicker than I thought. We were talking longer, but that's okay. Then, not to talk too much, I will state vertical and horizontal compositions in a usual way. Of course, I know them in a enriched way. This is an enriched diagram, we will see. But it will take right now too much time, and I don't have that formula, so it will be a little long. For right now, our purpose it will be enough.
I'm sorry, what is that notation? C to the D? Yes, yeah, that's just composition, right?
Yeah, it's a composition law in category D. So it should be F X G X G Y. Here it should be F X F Y G Y. So it's a composition, but every composition it has 3 labels, and also it has 4 labels where category belongs from. As I'm using the letter C for composition, so I don't know. You can use here / circle, so or just bubble. Then the following definition. If we have category C and category D, between them we have 3 functors F, H, G and H. Here we have natural transformation alpha. Here we have natural transformation beta. Then beta alpha is a natural transformation from F to H. With components. There will be arrows. F X to H X. Here will be composition. Beta X, alpha X, composition Morphisms. Of course, I can write through this thing, and once later we will see how, I hope, we will go in very much in details how to make an enriched composition. Vertical. And this beta alpha is called vertical composition of natural transformations alpha and beta. Okay. Next definition. It's called whiskering. So when we have a natural transformation between categories, it's called B, C. Here is functor F. Here is functor G. Here is our alpha. We can always compose it with functors that lay a little to the left or to the right. Let's call this functor M. This N. I wish the alphabet was longer. I so often have so big lack of letters. Okay, that's just my problems. Then I can define alpha m no, let's go with that. We don't need parentheses here. Alpha m as a natural transformation from MF, FM to GM, they are functors from A to C. You see how I wrote it? So natural transformation is a two arrow from functor to functor, and these functors are arrows, one arrows from A to C. So I wrote column and arrows twice. It's also one of the ways to write the things. What are its components? Alpha m. Components have indices in a category when it starts. A. That's it. So it's just this. Then I have n alpha. N alpha is multiplication by, composition of functor and natural transformation. When from what functor to what? NF to NG, from category B to category D. What are its components? N alpha, it starts with B, so sub B. It is N of alpha sub B. Who of them is called left whisker, who right? I never remember that. I really don't care. I know how to multiply it. One of them is left whisker, another is right. You can look up yourself. Definition. We have category A, category C. Here we have F1, 2, V1, here. V1, G2. Here is alpha, here is beta. Then define alpha, beta, horizontal composition alpha from V1 F1 to V2 F2 as functors from A to C in the following way. So I have V1 F1, and I need to finish up with G2 F2. I can go either way. Look here. I can go by this and then move using this stuff. And finally, it will be this function. Then in this function, I can change this part. And I then can get lower. Or I can take this again upper part, and in upper part, first move lower part. It will be this. And then in this function, I can move second part down. It's pretty much as a square. You can in square go one way or another way. So it will be 2g2 s1, 2g1 s2. Here it will be beta 1. Here will be g2 alpha. Here will be g1 alpha. And here it is. It is what? Theta. This triangle, square, commute. And the diagonal is called horizontal composition. Where you can see horizontal composition when you have 3 topological spaces, and you have homotopy between 2 maps, continuous maps here, you can make a common homotopy, where from 0 to 1/2, this homotopy changes here, and from 1/2 to 1, the homotopy changes there. So it's precisely how you glue together 2 homotopies. This is it. Adamant law, or it's also called middle form exchange or interchange law. We are finishing this right now. That's the last. So what is it? If you have a square, here is alpha, beta, gamma, delta. This square, you can write this way, or you can write this way. Here, alpha, gamma, beta, delta. Here, alpha, beta, gamma, delta. So we have delta, gamma, beta, alpha, delta, beta, this is picture 1, this is picture 2. So picture 2 equals picture 1. And as you see, I'm exchanging middle 2 and then changing all the rules. So it doesn't matter how to perform the composition. When you have a lot of blocks, of natural transformations, and you want to compose them, you can do them in either way. It's called interchange law, middle for exchange, and Gadaman law. So we haven't enough time today to define the 2 categories. That will be the next time. It's not that things that we need, but we are almost there. Thank you for attention. See you next week. Anytime you have questions, I'm every day on campus. You are welcome now. So, take care.
Thank you.